My name is Galen Mullins, and in this video I will discuss our work in accelerating the testing of autonomous vehicles using imitation learning. How to test and evaluate autonomous vehicles is a difficult problem facing the robotics community. As autonomous planning and control algorithms become more sophisticated, we need to improve our methods for testing them as well. However, it is difficult to apply simulation-based testing methods as many modern autonomous systems cannot be run faster than real time. This greatly limits the amount of tests that can be run in a simulation to get full coverage of the testing space. To solve the problem of a limited number of runs, we propose the following framework for creating surrogate agents via imitation learning. In this setup, a surrogate agent will observe the autonomy under test executing inside of a simulation and will use behavioral cloning to replicate its control policy and decision-making process. Our objective is to use this surrogate agent to perform a large sweep of the testing space and find those critical test scenarios which should be run against the expert agent. This process can be summarized in 3 steps. First, we run a small number of simulations with the expert in the loop to train the imitator agent using the Q-DAgger algorithm. Next, we use the imitator to run thousands of simulations sweeping the entire testing space. From these, we identify test scenarios where critical behavior transitions occur. We call these performance boundaries. Finally, we validate these identified performance boundary scenarios against the expert agent. In doing this, we reduce the number of simulations required by the expert agent from several thousand to a few hundred. But what is a performance boundary? These are scenarios where a small change in the environment can cause a large change in the autonomous vehicle's behavior. For example, by moving an obstacle slightly, we can change when the vehicle decides to return home. Scenarios on the performance boundaries represent the most informative test cases, as these are where the behavior of this vehicle is the most uncertain. We found that using the Q-DAgger algorithm, we could quickly replicate the navigational behaviors of the autonomy under test after only a few dozen training episodes. Not only this, but we found that a shallow multi-perceptron network was able to encode all of the performance modes of the target system, albeit with different levels of accuracy. As you can see, we replicate both scenarios where the vehicle was completely successful at its mission, ones where it returned home early, and ones where it collided with an obstacle. Here we have the results of running both the expert and imitator against a 2D testing space. If you compare the performance boundaries of the agents, you can immediately see that they coincide, indicating the scenarios generated by the imitator will be sufficiently accurate to test the expert system. Not only that, but we can estimate the accuracy of the imitator's behaviors by using boundary distance, as all the error areas are concentrated in the boundary region. We hope that we've piqued your interest and are looking forward to seeing you during the interactive session.